Thank you very much for the audience, for helping out, for the hardware. Prior to going to the content, I want to tell you who I am by showing you where I live. So this is a picture of my apartment block where I live. This was built in the 60s, early 60s, late 50s. And obviously a picture was taken on a sunny day, unlike today. And I will show you also the environment of this apartment block by showing you the distribution substation that supplies electrical power to my apartment block. The substation is about the same age as the apartment block. Obviously, when people move in, they need to have power to live there. So the left part of the picture is old, dated. What you see on the right is new. What is there is a loading station for an electrical vehicle. And that's there for less than a year now. And the issue is that when the house was built, obviously people didn't have in mind that it would be later on also the loading stations for electrical vehicles. So there might be a mismatch between the design of the distribution subblock of actually how it's being operated nowadays. The problem is a bit more universal. Here you have a newspaper clipping of how the power supply system is ever more being stressed in its operation. This is a problem that not only exists in the Netherlands, but also globally, also more worldwide. So how does this congestion system affect the distribution of power on the low voltage level? We have to deal with new loads, for instance, electrical vehicle charging, new infeeds, for instance, by wind farms or by solar cells or by local storage. We have the hardware of the past, which were built having the old specs in mind. And there's therefore a need for new simulation tools to be able to design and operate the existing hardware. And this is what the project aims at doing. And we target here the low voltage low voltage power transformers. What is a low voltage transformer? In its basic essence, it's a core made of ferromagnetic material, and it has two windings. It has a supply of power on the primary side, and you have a winding that requires the power. This is the load side. It is typically a low voltage winding. What you see here is a design with one phase. Typically, the system works with 3 phases. And you might have also more complex designs of the ferromagnetic yoke. But this what I show you here is the most basic design. What I want to do in my modeling approach is to explain how the power transformation works. So what I do is I make a model of the Maxwell's equations, most simplest form. So I introduce here the magnetic field and magnetic flux. To be able to solve that mathematically, I introduce the notion of a potential, and finally I arrive at a diffusion equation for the potential for the field. And my scope is to be able to solve this in a mathematical model, be able to later post-process for the losses generated in the windings in the core, to be able to subsequently be able to model the heat loss in the device. What you see here is a simplification. I left out all kinds of naughty details, because obviously the field will vary in time, particular frequency, and you have variation field. You also have electrical effects to take into account. Thermal management might be complex to deal with. There's the need to do the cooling of the device by oil in the transformer block or by ventilating the substation. And obviously we want to be able to see how the model performs, maybe also improve it by making a digital twin of the model and be able to use local information on the weather, for instance, to be able to improve the model. So what I saw before is simplification. In reality, obviously, I'm wiping things under the carpet in a first analysis. Now, this is a conference on Julia. Obviously, we want to solve the model in Julia. So one might say there are already excellent finite element solvers around. The GitHub and Ferrite are two examples, so why not just use those? I wanted to deviate from that path, be able to harvest on the entire Julia ecosystem, enough for everything that we have to be able to solve the problem. And I do this in collaboration with STEDIN, which is local DSO in my area. So this is maybe the most important slide of the talk. What I show here is the structure of the course that I teach using Julia with the design problem as motivation. The course has now 3 blocks. Block 1 of introduction, where I do 1D and 2D models in a simplified setting. Then I do a finite element variation formulation to be able to treat non-uniform meshes. And then I do the application. I try to apply the finite element method to be able to solve the potential equation for the magnetic field. And this is a course that spans 7 weeks. Roughly, the course is followed by 20 to 25 students at the master level. And the course material also serves me to bring the Julia also to other teaching that I do at the university. So what do I do in block 1, just to give you more specs of how the course has been designed. I do first the analysis in 1 dimension, because in 1 dimension things are easy to develop in the first instance. So I solve the Poisson equation in 1 spatial variable. I'm still thinking about a name for the package. So maybe something with fish inside it might be appropriate, maybe Flemish fish, given also my Flemish background. What you see here is the a problem without time. If you can do the time-independent case, later on you want to do the time-varying case as well, and maybe also the time-harmonic formulation. And I have examples in the course that allow us to do this. Okay, once we can do 1D, we can also try to move to 2D. What you see here is a cross-section of the transformer that has a middle leg and two side legs, and around these legs the windings are being applied. Please remember that the configuration has a middle leg. This will be important for the future of the talk. On this mesh, so we have here a set of elements forming the mesh. On this mesh, we want to construct the discrete problem. So therefore, the matrix and the vector, by doing a loop over the elements. So therefore, doing a global assembly by looping over the elements individually. And we needed some time to figure out how to do this in a stable manner, but now we have arrived at it. We are trying to further explore the assembly part of the code by looking at issues as lazy objects or using it as a map to be able to arrive maybe at a more readable implementation. I'm happy to have feedback on that. The use of AD tools discussed in the previous talk to be able also to do optimization and to treat nonlinear materials. How to make the code to be more generic, working for 1 and 2D, or maybe also working for different orders of the implementation. And doing a parallel implementation either in shared memory or distributed memory. So interest that I would have to be able to speed up the model and bring the model to a digital twin environment. We have also issues on the linear solve, looking at issues as comparison between direct and iterative solution methods, and using legacy code such as the PETSI library to be able to accelerate the code overall. I will now show some sample results of what we are currently able to do. What you see here is the computed magnetic flux in the configuration you saw earlier. So here we see a snapshot of how the field distributes in the geometry. And what you see next is a more detailed analysis of what happens in the central leg of the transformer. One issue is the fact that with these new devices, we expect to see higher frequencies in excitation. And what they're trying to simulate here is the effect of the higher frequencies on the operation of the device. So the picture shows a left and right subfigure. The left is what happens if we simplify the model to have a linear magnetic behavior, and therefore we have a given flux distribution in the core leg over time, and this looks fine. If we switch from left to right, we will see that we see two effects. The fact that the flux is lowered, this is the saturation effect, but also there is a shaving off of the peaks. So if you shave off the peak going from left to right, what will happen in a frequency domain is the occurrence of higher frequencies. So what I show in the picture over here is again a comparison of linear left with nonlinear right, and the fact that due to higher operating frequencies, also the frequency in the flux distribution increases. What this means is that in the transformer, you might have higher losses, and therefore locally you have an increase of peak temperature, and this might be damaging for the whole device. And therefore the interest to be able to capture these peaks in a realistic fashion. Okay? To conclude, I talked to you about a problem in industry, that is how to model transformers in a distribution network. How I take this problem in an educational setting, in a course on the Finite Element Method, and how this dialogue between industry and students is shaping the course overall, and how we're able to bring in Julia in an environment that encompasses both industrial research and education. And I'm happy to receive feedback on how to improve the code further. Thank you very much.
Okay. Now we have plenty of time for questions. So.
Thanks for your talk. I'm delighted to hear you use Julia for educational purposes.
Okay.
I wish I've been a student. This was around, I think, 25 plus years ago when I took these kind of courses. My question is, if you do this finite element kind of work, the whole secret is also about the gridding. You know, you need to have fine grid where a lot of changes are ongoing. You can do with a coarser grid. So what are you using for gridding here?
Thank you very much for your question and your feedback. It's indeed sad that at times the academic settings is slow to evolve, let me put it that way. You mentioned the issue of how to do the mesh generation. If you, what you see is that due to the higher frequencies, you have locally strong gradients in the flux that need to be resolved well. Therefore, if you look very carefully into what we did over here, this mesh was not generated by coincidence. We know a priori from analytical computations where the flux will concentrate, for instance, at the sides of the core lake due to skin effects, and therefore do there a priori a local mesh refinement. So this is already taken into account in the simulations.
What did you use to generate this mesh? Because this is also an adaptive mesh with quads and...
This is generated using Gmesh.
Gmesh, okay.
Yes.
Nice.
But then it's manually generated by the knowledge of the person.
Exactly, yes, true. This is done because obviously these computations have been done before. We're not the first ones to do this, so you kind of expect issues to appear and take the precautions. That's true. In a more evolved version of this, you would like to be able to discover where the flux will concentrate and do adaptive mesh refinement. And this is on the to-do list for future code developments. For instance, the ferrite people who are also here are looking into adaptive mesh generation in their implementation. I don't know whether the Trixie people are doing the same. They're at the back. We can discuss with them. So, but it is indeed a very relevant issue to point out.
Okay. Another question?
Yeah, thank you for the talk. It's awesome to see finite elements showing up. I'm a bit curious about your software choices. So you mentioned in the beginning that you decided not to use the finite element frameworks that we have available in the language. Was that a choice for pedagogic reasons? And what do you do in the course? Do you have the students write like everything from scratch? Is it a somewhat specialized code for what you're doing then, or why did you make that choice?
Thank you very much for your questions. These are relevant questions to answer. The choice to stay away from prepackaged stuff is to be able also to expose what really goes on to the students, right? So I deliberately build up stuff step by step, and I also take time in block 1 in the lab sessions to teach them how to use Julia. And you're starting, because Julia is new, right? The bulk of the education still relies on non-Julia tools. So also we want to take time to introduce Julia in the lab sessions. And block 1 allows space for that. I tried to use the Trixie code in the master course in April. And I discovered that students have a hard time digesting Julia. They see type definitions, they don't know what they mean. So if I start immediately from day 1 with Trixie or with Ferrite or with GitHub, the students are confused because they need guidance into the language of Julia. So that's what motivates doing it in a step-by-step way.
Yeah, thanks again for the talk. I was wondering, is there something that conceptually holds you behind doing unsteady simulations? So because, I mean, OrdinFAQ makes it super easy to like just, formulate your FEM model like as a function. You need initial condition and you send it over to ODE-DFAQ.
There is indeed a good suggestion, and what I show here is indeed the time-independent situation, but I also do the time-variant case as well in the lab sessions.
Ah, cool. But are you then also implementing like your own ODE solver, or how are you doing this?
Not yet. We are relying on the tools that DFAQ does provide to do the time varying case. However, in reality, the transient case is difficult because we also have to take into account the algebraic constraints coming from the circuit. So we also have to have the DAE solvers to be able to do the transient simulations.
Okay, thank you.
I could see you're talking about solving the coupled problem. I was curious, are you solving the thermal model directly on the grid as well as the EM in concert? Are you doing that together?
Not at the moment. At the moment, we are cheating for educational purposes. It is, we solve what you see here 2 times in a row. We do first U being potential for the field, post-process, arrive at sources for heat, and then do it again where U is a temperature.
Okay, so just a one-to-one.
Yeah, exactly.
Okay.
However, obviously, we are aware of more complex approaches, obviously.
Yeah, thank you.
One question?
Yes, so you mentioned that you have these higher frequencies, higher harmonics occurring at magnetic saturation.
Yes.
In which condition does this magnetic saturation occur?
Excuse me?
Under which conditions does this magnetic saturation occur? Is it like if I use this transformer at higher energies or higher?
Yes, true. The question is about when does saturation happen? So the coils are wound around a core of iron, and that iron has its physical properties. You can compare it to a sponge. A sponge that absorbs the water. However, if the sponge is wet, if the sponge is fully soaked, it doesn't absorb the water anymore. Same as here, right? If you saturate the material with magnetic flux, at a certain point it will no longer be able to take it up, and therefore there will be a fringing flux through the air.
Thank you for the talk. Are you modelling eddy currents as well in the simulation as part of that? And are you, I was thinking particularly in reference to the higher frequency components, are you including the skin effect?
Yes, we are. Yes.
Okay.
I have one question myself.
Okay.
So since you are using this to teach Julia, thank you very much for that. I wonder what's the usual struggles that students have by learning Julia, the language.
Okay. Okay. I can tell you the good news first. When I introduce Julia in a teaching, students are happy to go along with that. They don't complain about it. And I teach now different courses using Julia. In the course that I show here, there is a place to introduce Julia. Right? There is a first lab session of 4 hours. There's lots of documentation. There's Jupyter notebooks. They can go play around and you learn stuff as they go, which is wonderful. That's fine. That works. What doesn't work is at the master level, giving a project-based assignment on simulation and modeling, hoping that they will learn Julia from the out of the blue. You need to give them more guidance. And what I encounter there is, as a struggle, is the fact that Julia is a typed language, and students don't know anymore what a typed language is. They come from Python, they come from MATLAB. Why do you define types? That's one struggle.
So types is usually the main problem.
Yes.
Okay.
At least in my experience.
Okay. Something else, maybe documentation, maybe.
Documentation, yes, but that's a bit universalist, I think. But there I try to compensate by writing bits on my own.
Okay.
How do you use Gmesh? Okay, fine. We managed to generate the mesh. Wonderful. After efforts, installing it, making it run. Good. Finally are here. Then comes the issue of how to do a traversal over the mesh elements. And obviously, if you know Gmesh for ages, you do it fine, but for students, it's new.
Okay. Okay. Yeah. Okay. I can see that. Okay. Thank you very much. So I think that we should just thank our speaker, and we will have.